So I figured because we don't really have time in our semester schedule to set aside for like a review day before each of the exams, I kind of feel bad about that because I usually like to do a review day before the exam. To sort of compensate for that, I decided to just make a video where I do a little bit of review. I'm going to go through this practice exam that I posted. And I think that the practice exam covers like a good bit of the material that you need to know. Like there's definitely like some gaps in here. Like if you only study this, then you will probably like run into some issues on the exam. So definitely like I recommend first and foremost like going through all of the guided notes and making sure that you understand everything in those guided notes. Also read through the textbook. I would like go in detail into either the textbook or the guided notes and then skim the other one, just to make sure that like you're familiar with like everything and all the concepts that sort of show up. From there, I definitely recommend spending a lot of time doing practice problems. So if like say for example in let's see worksheet, here's section 4.6, maybe in this section, the variation of parameters, you were not so sure what was going on with like some of these things and you felt like you needed more practice with like, you know, computing the Wronskians and then W1 and W2, and how to apply all the formulas. I put some practice problems at the top of these. So if you want some extra practice for anything, I would recommend kind of going through these. Maybe I would say do these rather than spending time on the web work, because sometimes the web work problems can be a little bit more complicated, but definitely make sure that you understand all the examples from each of the guided notes, and from the practice exams, and then use those extra practice problems as extra practice. Okay, I included a bunch of like formulas on the practice exam, and these are the formulas that you're going to see on the exam on Thursday as well. I'm not including like what each of these formulas like are used for or anything, but you should be able to sort of recognize like this right here. This is the reduction of orders formula. I'm not telling you the context behind this, but you should just kind of know that like the context is you are given or you know what y1 is, what like a first like solution is. So you know one solution to your differential equation, and then this is a formula for your second linearly independent solution to your differential equation. Quadratic formula. This right here is your variation of parameters formulas. There's sort of a lot of things that could be like included in the variation of parameters formulas, but this is the one that's like most helpful to me. I'm not including like the formula for what W and W1 and W2 are, but they're, you know, W is the Wronskian. You should know the Wronskian. W1 and W2 are the Wronskians, but you replace like the first column or the second column with your answer column, where you have like 0 and then f of x for your answer column, where f of x is like whatever is the you have like y double prime plus blah 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 blah, and then f of x is whatever's on the right hand side. This up here is the formula for if you have a what's it called, logistic equation. So when you have like dy dt is equal to, it's proportional to y times like m minus y, something like this. So it's proportional to like the population present and then m minus the population. So m is like your carrying capacity. I probably should have used p's instead of y's here, but whatever. So this is like the formulas for like the for that. Right. So yeah, you're just allowed to, you don't have to like take that logistic equation and then like show how to get to these formulas like from scratch, you can just kind of like utilize that to get your formulas. All right, let's kind of go through, and then if I start feeling like it's getting too tedious or I'm spending too much time on stuff, I might just kind of skip it and then post these solutions like separately, and then just kind of talk about like sort of the main things. That might happen with this one because I think this is going to be a logistic equation one, and these ones are kind of long. So suppose that 5 students come back to campus after a summer break with a new strand of virus. Assume that the campus is isolated with 20,000 students, and the rate at which the virus spreads is proportional not only to the number P of infected students, but also to the number of students not infected. So that line right there is telling us like dP dt is proportional to population P times the number not infected. So if there's 20,000 students there, then 20,000 minus P are not infected. So this is just straight up telling us that it's a logistic equation. And so it's also telling us that after 5 days that there are P of 5 equals 60 infected students. And there are 5 students that come back with the virus. So like initially there are P of 0 equals 5 things right there. So this is like our initial population of like infected students, whatever. All right, so we are just going to utilize these formulas up here. So I'm literally just going to copy and paste them and bring them down just for reference. We're totally going to run out of space on this one. Okay. Let's figure out what C is first because we're going to plug C into this thing anyway. So C is equal to our initial population, which is 5 divided by M minus our initial population. M is our carrying capacity, which is 20,000, because you can only infect up to 20,000 students on campus, and minus 5. This is going to be 5 over 19,995. Okay, great. Terrible number, but whatever. You could probably simplify that. I'm sure you could. Maybe I will, just for simplicity. Let's go to a calculator. Please no ads. Okay, 19,5 divided by 5 is 3,999. Oh, I should have been able to do that in my head. Whatever. Because like 20,000 divided by 5 is 4,000, and then it's like one group of 5 less than that, so it should have been like 1 less than 4,000. Whatever. All right, so that's our C value, and so our P of T is given by M times C. M is 20,000. This is our C value plus e to the negative mkt. K is unknown, so now we need to figure out what K is. Also, it's probably easier to just multiply through by 3,999 on the top and bottom. You get this if you do so. So this just cleans up the formula a little bit. Makes it a little easier to deal with. Now P of 5 is equal to 60, and so this is telling us that 60 is equal to 20,000 over 1 plus 3,999 e to the negative 2,000 kt. At this point, we just need to sort of solve for, sorry, not t. This is P of 5, so this is telling us that t is equal to 5. All right, so now we just multiply through. So 60 times 1 plus 60 times 3,999 e to the negative 2,000 k times 5. 2,000 times 5 is 10,000 k. This equals 20,000. subtract over 60, and I get 19,940. And then I'm going to divide by the 60 times 3,999. Is equal to e to the negative 10,000k. So then, taking natural log of both sides, we get negative 10,000k equals natural log of that right-hand side. Too many nines. And then we're just going to divide by negative 10,000 and get that k is just equal to this whole thing. Oh gosh, don't erase, just wanted to put parentheses around here to clarify that. So that's our k value. So this tells us what p of t is equal to, or this is what p of t is equal to. And so now we just need to figure out what population is after 14 days. That's p of 14. So that's 20,000 over 1 plus 3,999 e to the negative 20,000. Or is it 20,000 or 2? I missed a 0 up here. That should be 20,000. 20,000 times k, which is what we're dividing by, like negative 10,000 times ln of, oh gosh, running out of space. All right, and then times our t value, which is 14. So this is terrible, but this is just what it is. So you could put this into a calculator and it'll estimate it for you. Maybe I'll do that later when I post these separately. Maybe I'll forget. Who knows? Okay. How many days does it take for the number of infected students to reach 1,000? So now we just take our p of t value and we say, when is p of t equal to 1,000? And so our p of t formula is 20,000 over 1 plus 3,999 e to the negative 20,000 times k, and 20,000 times k, kind of like over here, 20,000 divided by 10,000 is equal to 2, and the negatives cancel out as well. So we get 2 natural log of 19,940 over 60 times 3,999. And then we keep the t there, set this equal to 1,000. And then we just solve for t. So I am just going to skip that now. I'll post the solutions for this later, but I don't think it's really necessarily worth kind of going through because these are just sort of algebraic steps, but I'll post them later. All right, tank is filled with 50 gallons of pure water. Water with 2 pounds of salt per gallon is being poured into the tank at a rate of 5 gallons per minute. Find the number A of t of pounds of salt in the tank at time t. Okay, so what we need to do here is set up a differential equation and use that differential equation to solve for this function a of t. So what is dA dt? So a of t is the number of pounds of salt in the tank. And so if we are, we're starting with pure water, and then we're adding sorry, I think I just realized that there's a typo in this. Okay, this was supposed to be very similar to the 3.1 problem. So I'm just going to modify this on the fly. Where is 3.1? Worksheet 3.1. Yeah, it's missing this sentence right here. Then the well mixed solution is pumped out at some rate. So I'm going to copy that over, and we're just going to bring that along with us, and then I'm going to modify this after I post this. So really we're trying to say the well mixed solution is then pumped out at a rate of some number of gallons per minute. Yeah, let's just keep it at 4 gallons per minute. All right, so the water is being added. So, all right, so we're adding salt water, and then we are pumping out water as well. So if we're adding in if we're adding in salt water and then removing some of the well mixed solution, then we're still going to be like adding salt, but we're also going to be like removing a little bit of that at a time as we're pumping out 5 gallons or pumping out 4 gallons. All right. So what is the rate at which salt is added in? This one's more straightforward. So we're adding 2 pounds per gallon at a rate of 5 gallons per minute. So this is 10 pounds of salt per minute. So dA, this is like change in pounds of salt. dt, this is like change in time. So we should be getting change in pounds of salt over minutes. So these have the correct units, and so this seems good. So our rate at which salt is being pumped in is 10 pounds per minute. All right, what about the rate at which salt is leaving? This is the harder part, which is why I'm upset about the typo. All right, so the solution is being pumped out at a rate of 4 gallons per minute. So we are, let's see. So we're pumping out 4 gallons of water per minute. But how many pounds per gallon are we going to be, is like how many pounds of salt is there going to be per gallon at time t? Okay, well, at time t, it's going to be total number of pounds of salt divided by total number of gallons of water at time t. So what is the number of pounds of salt at time t? So we can't like say what this is explicitly, but A of t is just like that function. So A of t is the number of pounds of salt in the tank at time t. And how many gallons of water do we have at time t? So we start with 50, right? So we're starting with 50 gallons of water, and then water with 2 pounds of salt, blah, blah, blah. Okay, so we're adding 5 gallons per minute, and then we're pumping out 4 gallons per minute. So we've added, so each minute we add 5t gallons, and we pump out 4t gallons. So this is equal to 50 plus t. So let's change that to just A of t over 50 plus t. Maybe I'll make that A of t. Okay, so this is 4a over 50 plus t. So dA dt is equal to the rate at which it's going in, which is 10 pounds per minute, minus, we're rate at which it's going out, which is 4a over 50 plus t. All right, how do we go from here? All right, so there's a couple ways you could do this. You could try to see if it's separable. It looks linear to me though, so my first thought would be bring this 4a over 50 plus t to the left-hand side. Write this as 4 over 50 plus t times a. It's equal to 10. So this is basically like y prime plus p of x times y is equal to q of x. So it's like a linear differential equation. So it's just sort of this form. And so then you just need to figure out what your integrating factor is, multiply both sides by your integrating factor, which should really be like mu of t because our input variable is t. So this is e to the integral of p, which is 4 over 50 plus t dt. This is, I could bring that 4 out, and then natural log of 50 plus t, and this is equal to 50 plus t to the 4th. Great, so now we just multiply by that on both sides. Oops. We're dividing by 50 plus t there. So this would be 50 plus t to the 4th divided by 50 plus t, so to the 3rd. This left-hand side now becomes, we reverse the product rule. This is d dt of 50 plus t to the 4th times a, and then you usually would want to check that if I do product rule, derivative of this is this, and then derivative of this is this. Sorry, not the dA dt. Oh wait, sorry. Derivative of a is dA dt. Okay, so good. So this does reverse the product rule, and then we get this on the right-hand side. So now we just integrate both sides with respect to the same variable, and we get 50 plus t to the 4th times a is equal to 1/5 50 plus t to the 5, and then times 10. 1/5 times 10 is equal to 2. So then a would be equal to, and then plus c as well. So then a would be equal to 2 times 50 plus t to the 5th divided by 50 plus t to the 4th. So this would be to like the 5 minus 4. And then plus c over 50 plus t to the 4th. And then you just need to figure out what c is. How do we figure out what that is? Well, we have our initial condition of a of 0 is equal to 0. And so we can say 0 is equal to 2 times 50 plus 0 plus c over 50 to the 4th. And so then from there we can say, let's see, that'd be negative 100, or negative 2 times 50 to the 5 is equal to c. So you solve for c, this would be your c value, and then so a would be equal to 2 times 50 plus t plus, or I guess it'd be minus 2 times 50 to the 5th over 50 plus t to the 4th. All right, so a little bit long, but that's how you do it. All right, this will be like the last chapter 3 thing that happens here. Let's see, maybe I'll just go quickly through this one because chapter 3 is not going to be as emphasized on the exam as chapter 4 will be, because there's just inevitably more chapter 4 material. There just happened to be a lot of chapter 3 things that I could ask about. All right, recall that the rate at which the temperature of the body changes is proportional to the difference between the temperature of the body and the temperature of its surroundings. So this is saying the temperature, d time, is proportional to the difference in the temperature of the body with the temperature of its surroundings. So I'll call that like T sub 0, I guess. So we have a steak that's removed from a pan, and its temperature is measured at 135 degrees Fahrenheit. 5 minutes later, it's at 100 degrees. So this is telling us T of 0 is 135, and T of 5 is 100. We're assuming that little t is in minutes, and capital T is in degrees Fahrenheit. The temperature of the room is 70 degrees, so that would tell us that this is going to be 70. And we then want to know how long is it going to take for the steak to cool to 85 degrees. All right, so this one is more straightforward. You take this differential equation and separate it. So 1 over t minus 70 is equal to k times dt. Then you can sort of integrate both sides with respect to, oh, I forgot the dt over here. Yeah, okay, so yeah, now we can just say this is equal to this, and then integrating both sides, the left-hand side is ln of t minus 70. The right-hand side is kt plus c. T of 0 is 135, so if I plug in little t of 0, that should tell me that capital C, so k times 0 plus c is on the right-hand side, and now ln of capital T minus 70, 135 minus 70 is 65. So C would be ln of absolute value of 65. Maybe it would have been smart to do e to the power of both sides first, but I didn't. Okay, and now we also can say, to figure out k, we can do t of 5 is 100. So ln of 100 minus 70, which is 30, is equal to k times 5 plus ln of 65. Yeah, definitely should have done e to both sides first. Oh, actually, no, it's fine. All right, so this is ln of 30 minus ln of 65. I don't really need these absolute values here because they're already positive. Log rules, this is equal to ln of 65 over 30. And so k is equal to a fifth of that. So then we have ln of t minus 70 is equal to k times t plus c. E to both sides. This becomes I'm sort of doing log rules in my head. Then times 65. So then t is equal to 70 plus 65 times 65 over 30 to the 5t. Anyway, sorry, I'm skipping steps right here for the algebraic parts, but the setup and then the, understand all like the differential equation stuff, that's all like sort of the main stuff that you need to be aware of. Okay, that's pretty much it for like all the chapter 3 material. If you understand like those types of problems, that's probably going to be like most of what I would do. I don't think I answered everything in this problem even, because we're asked like when is t of t equal to 85. So literally all that we have to do is like set this equal to 85. and then solve for t. So I'll like post the solutions for this in a bit. So I'll end this part of the video here and then split this into like, you know, these are the chapter 3 things to know, and then you'll have like the chapter 4 things to know. And yeah, this is probably a little too long, but I'm doing this in one take, so you get what you get.